So as I was saying in the previous video, cold air is denser than warmer air, right? Warmer air is going to have less pressure. So this can be seen pretty much in the figure to your left. This kind of represents the different latitudes at which that we have on Earth and the different pressure systems that we are seeing. So for example, let's take the equator as our example. We know that it is pretty warm overall. And so you're seeing that it usually has a low pressure system. So again, solar heating and evaporation of that seawater at those low latitudes is happening near the equator. And by this evaporation, it's creating warm and low density air masses that then have a high relative humidity, right? The moisture tends to be pretty high. So then this warm, low density air that is near the Earth's surface creates these low pressure zones. So that's what you're seeing here on the left part of the image. So those low pressure zones at the equatorial latitudes then will convect upwards into the atmosphere. So the heat will basically rise up, goes from high heat to low heat, remember, and it will convect upwards into the atmosphere until it reaches a certain height, at which it will start to basically condensate. It will go from being vapor water to being liquid or even solid water, right? So that's where you have that latent heat, that change in phase. Okay, so you're seeing that is happening somewhere up in the atmosphere. You have that change from water vapor into precipitation, and then you have the specific zones basically move into higher pressure and colder, for the most part, regimes. Okay, so you see that the high pressure systems, which tend to be this kind of mid latitude between I guess what would you call that, low to mid latitude point, is where we have this high pressure systems, which tend to be colder systems. Okay, and that is where for the most part you have the precipitation of that warmer air and moister air mass coming down and going downwards in that convection kind of cell. All right. Let's see. Yeah, okay. So again, that precipitation that you're seeing there in the high pressure system is pretty characteristic of the lower latitude kind of tropical area. So 30 degrees latitude is places, for example, like Florida. So you have a lot of precipitation going on there, right? Places like Central America for the most part. You have a lot of precipitation going on there. Same thing for the Amazons, for example. That tends to be kind of like around here, this kind of 15 to 20 degree latitude to the south. You have a ton of precipitation undergoing at that place too. In India, for example, you get some of that from the northern part as well. So those are characteristic of it. Again, lower pressure with warmer climate or warmer areas, and then colder pressure, or sorry, more higher pressure with colder areas. So having those things in mind, again, you have from the previous slide, I guess, you have that low pressure, pretty moist masses going upwards into the atmosphere, then precipitating down into like the 15 and 20 degree latitudes. And then that dry, cold, and dense kind of air that is at the upper troposphere now moves towards, each pole, and it basically sinks into the higher pressure system. So it sinks at about 30 degrees in latitudes, right? So it's going to be the subtropical high and subtropical high in the south. Subtropical high in the north, subtropical high in the south. So it is no coincidence that at those specific latitudes is where we have the major deserts in the world. So because we have that dry, cold, and dense air coming down, which causes also a fair amount of wind patterns, which we'll talk about later. But basically, if you think about the main deserts that we have, In the Americas, we have the Mojave Desert, the Chihuahuan and Sonora Desert in Mexico. And then in the south of the Americas, we have the Atacama Desert, for example. Also in Eurasia and I guess Africa, we have the Sahara Desert, right? We have the Gobi Desert in Mongolia, the Arabian Desert. Um, and then as part of the like Oceania part, we have the Australian deserts. And also in Africa, we have the Namib and the Kalahari Desert in the southern part of Africa as well. So all of those deserts that I described just now fall within that 30-degree or so latitude, which is where the dry, cold, dense air masses fall. So that is no surprise. The same kind of phenomenon happens at kind of mid to high latitudes. You have that subpolar low either on the north or on the south. That basically has these low pressures then rising towards higher pressures. So eventually you're going to get, again, precipitation somewhere in between them, and you're going to have the low pressures going either towards the like really high poles or towards the 30-degree latitude. So you're going to get going from lower pressure in that mid to high latitude to lower or to higher pressures in the 30-degree latitude and the 90-degree latitudes. Okay? And so that's also partly why we have the deserts at the 30-degree latitudes and why we have deserts in the poles. So as you might know, the poles, especially Antarctica, is just a major, major desert. Yes, it's super cold, so we haven't explored it fully, but it is a desert nonetheless because of the same phenomenon of that dry, cold air rising and, or I guess, coming down onto those higher pressure systems. And in this mid-latitude, different air masses of different temperatures are going to collide near the tropopause. So at that very high limit of the troposphere, you're going to get air masses of different temperatures to collide, and those are going to cause kind of like a discomfort, if you would, at that higher part of the troposphere, sorry. So due to that discomfort, you're going to create what we call the jet streams. So the jet streams are going to be, again, very high in altitude. I'll go through them a little bit more in the next slide. But they're going to be near the tropopause, and they're going to be, or they're also known as westerly winds because they go from west to east, either in the South Pole or in the North Pole. They still go west to east. So they play an important role in the path that storms take nowadays, and so that's something to take in mind. And their west to east movement is actually due to the Coriolis effect, which I will also go over in a couple of slides. So something to have in mind is that the greater the temperature differences between those two colliding air masses, the faster that the jet stream will flow. So if I have a very warm air mass colliding with a very cold one, then my jet stream is going to be very, very fast. If I have two masses that only are maybe like 2 degrees Celsius apart from each other, then perhaps that jet stream is not going to be as fast as it could be. Okay? So there are two main jet streams, two in the south and two in the north. So they're going to be the polar jet stream is going to be the I guess northern and southernmost part of the jet streams, and then the subtropical jet stream, which is going to be closer to the tropics, either in the north or in the south. Okay, that makes sense. So the polar jet stream is going to be the strongest out of the two, and it changes courses from summer to winter, as we're seeing here in this diagram on the bottom left. So you're seeing that the orange line shows you kind of the path of the polar jet stream during the summertime, and then the blue line kind of shows you the path of the polar jet stream during the winter time. The subtropical jet stream also changes paths, but not as strongly as the polar jet stream does. However, for both of them, they're gonna be stronger or faster. They're gonna be faster, have a higher velocity during the winter than they do during the summer. And again, that's depending on which pole they're at. So obviously in the North Pole, they're going to be strongest during our winter, which is going to be in December, January, February. And then the South Pole is going to be strongest during their winter, which is going to be in the May, June, July, whatnot. Okay, so these jet streams are going to vary in width between 100 and 500 kilometers or so, and they're going to be several kilometers in thickness. So the average speeds of them, or at least of the polar jet stream, is going to be 180 kilometers per hour during the winter and about 90 kilometers per hour during the summer. So again, a lot faster during the winter. The peak flows that they have is usually twice as strong as the average flow. So the fastest that the polar jet stream flows, for example, during the winter is about 360 kilometers per hour, which is incredibly fast. Usually cars here in Boise are traveling about 100 kilometers per hour in in I-84. So that kind of gives you an understanding of how fast this really is. So these jet streams, both the subtropical and the polar jet stream, kind of cause that phenomenon that you see when you fly, that flying westward takes a lot longer than flying eastward. So that is because, for the most part, airplanes are traveling at the same altitude that the jet streams are happening. So because these are westerly winds, meaning they go from west to east, they're going to provide a lot more friction as the airplane goes from east to west, right? So flying westward usually takes longer than flying eastward. You can notice that if you have a round trip going to anywhere in the east, usually it's going to take you easily, maybe, like if I'm going from Boise to, I don't know, Raleigh, North Carolina, then it usually takes me at least 30 minutes more coming back to Boise than going to Raleigh. So that's something that you guys can notice next time you fly east. Okay, yeah, and again, the polar jet stream is going to be the strongest out of the two because there's greater temperature differences in the air masses in that specific jet stream. So the different air movement can also cause changes in atmospheric pressure overall, creating this convergence and divergence that you're seeing there on the slide. The combination of temperature and air movement will produce pressures that are either low pressure or high pressure, as we have seen before. And so these combinations of high pressure systems create what we call ridges and troughs. So ridges are going to be where there is local high pressure or local high pressure. So you're seeing here on the diagram, a ridge is happening where you have high pressure. And then the troughs are going to be where you have low pressure for the most part, right? Okay. So these local activities sometimes is really what makes the jet stream kind of shift around, as we saw in the previous image. So you saw that it shifted, as you go from east to west, not necessarily always in the same pattern, but it is still shifting. And just to kind of relate terms, the convergence is going to be overall flow of air that is coming into a region. So the air is piling and the pressure is increasing. So is where you have high pressures. So things are coming together, convergence, high pressure, making ridges. So you're building up pressure. And then divergence happens when you have overall flow of air leaving the region. So you have air loss, lowering of pressure, and you have troughs. So that makes sense. Lowering of pressure, you have a trough as a result of that. And then you have, overall less pressure. What did I say before? Yeah, air is leaving that specific spot. Okay, so remember, pressure flows from low pressure into high pressure. From low pressure areas is going to be divergence. Towards high pressure areas, you're going to get convergence. At those low areas, you have troughs, and at the high areas, you have ridges. All these things are going to be in your quizzes, so make sure that you can relate the terms and associate them to each other, okay?